In this video, we're quickly deriving a formula for the energy density stored in a magnetic field, and we're going to do this in the context of a solenoid or long coil of wire. So we know a couple things about the solenoid, and the first is that the magnetic field is given by B equals mu naught little n times I, where that little n is actually the turns per unit length. So we can replace that little n with a big N, the total number of turns in the solenoid, divided by little l, which is the length of the solenoid. Next, we derived the inductance of a solenoid by using Faraday's law, and we arrived at this expression. So big L, that's the self-inductance, or just the inductance of the solenoid, is given by mu naught times big N squared times A over little l, where again the big N is the total number of turns, A is the cross-sectional area of the solenoid, and little l is the length. Finally, and this is true for any inductor, the energy in the solenoid is given by 1/2 big L times I squared, where again that L stands for the self-inductance of the coil. So now we're going to make a critical shift in perspective and say that another way to look at the energy in an inductor is to say that it's stored in the magnetic field. This is reasonable because there's only a magnetic field in this thing when there's a current flowing. In other words, there's a direct relationship between any particular current value and the strength of the magnetic field in the solenoid. So the plan is to pin the energy in this solenoid on the magnetic field that's permeating the volume inside of it. So we start by looking at the total energy. So there's our total energy expression that's valid for any inductor. And then we're going to divide by volume on both sides to convert to an energy density. And with this step, I've introduced this new symbol, little u, that stands for energy density or energy per unit volume, and it's measured in joules per cubic meter. So the energy density inside of this solenoid is given by 1/2 Li squared divided by the volume inside that solenoid. So in the next step, we're just going to plug in the inductance of a solenoid for L, and we're going to plug in the area times the length, which gives us the volume of the solenoid down there in the denominator. So this first fraction right here, that's a simple replacement of big L with the inductance of a solenoid formula. And again, down here, we just replace the volume with area times length. So we notice that the areas are going to cancel out, and we can clean things up a little by turning this all into one fraction. So at this point, we have 1/2 mu naught big N squared I squared over little l squared. And what I notice is we're really close to having the magnetic field of the solenoid squared in this expression. So going back to the expression of magnetic field as mu naught big N I over L, if I square that, I get all the same stuff as I get down here, except I need my mu naught to be squared. So what I'm going to do is multiply the top and bottom of this expression by mu naught. So now I've deliberately built an expression over here on the right-hand side that's actually just the magnetic field in the solenoid squared. And the side effect is down here. I had to multiply the top and the bottom by a factor of mu naught. So now I have a mu naught in the denominator. So finally, we can say the energy density through the volume of this solenoid is 1/2 mu naught times B squared. So of course the solenoid is a special case, but it turns out this actually is true in general for any magnetic field. There's an energy density associated with magnetic fields, just like we showed previously for electric fields. And this perspective can be really useful for solving certain kinds of problems. In the next video, we exploit the magnetic field energy density to compute the inductance of a coaxial cable. And this approach is conceptually much cleaner than attempting a direct Faraday's law approach. I'll post a link to that video at the upper left, and I'll see you there.